Every single thought you have, every memory you pull up, even the feeling of your own heartbeat. It's all the result of a conversation. A silent, lightning-fast conversation happening trillions of times a second between your brain cells. So today, we're going to pull back the curtain and listen in on how they actually talk to each other.
So let's just start with a number that's, well, it's pretty hard to wrap your head around. Your brain is packed with about 100 billion neurons. That's more than 10 times the number of people on planet Earth, and every single one is like a tiny, living computer chip.
And these neurons, they're not working alone. Not at all. They weave together this incredible tangled web with trillions of connections. It's this network that powers, well, everything you are and everything you do. But here's the really weird part, the central puzzle we need to solve.
Even in this super dense network, the neurons never physically touch each other. There's always this tiny, tiny space separating them. So if they aren't directly wired together, how on earth does an electrical signal get from one to the next? How does it jump that gap?
Well, the answer to that question, the real hero of our story today, is this incredible little structure called the synapse.
The word synapse actually comes from Greek, and it means to clasp together, which is just perfect. It's this special zone where two neurons get incredibly close enough to communicate, but they don't actually merge. They remain two separate cells, just holding hands, so to speak.
Okay, so let's picture the journey. You've got this electrical signal. It's called an action potential, and it's racing down neuron A. It gets all the way to the end, but now it's standing at the edge of a cliff. To get its message over to neuron B, it has to find a way to cross that gap. It can't just jump.
So what does it do? The brain actually has two main strategies. There's a small number of what we call electrical synapses, and they're like a direct connection. Ions just flow right through. They're super fast, but they're also pretty simple. But the vast majority are chemical synapses, and that's what we're going to focus on. These are way more interesting. Instead of a direct wire, they do something amazing. They convert that electrical signal into a chemical.
So let's do it. Let's zoom right in on one of these chemical synapses and take a look at its parts to see exactly how it pulls off this amazing trick.
Every chemical synapse has three basic parts. First, you've got the sender neuron's end, which we call the presynaptic terminal. Then there's the gap itself, that's the synaptic cleft, and then, right across the way, you have the receiver, the membrane of the next neuron, called the postsynaptic terminal. Sender, gap, receiver. Simple as that. Now, if you look inside that sender terminal, it is just buzzing with activity. You've got mitochondria, which are like little power plants, making sure there's enough energy for all this to happen. And then, most importantly, you see these tiny little bubbles. They're called synaptic vesicles. Think of them like little envelopes, and each one is stuffed with thousands of molecules of the chemical message, the neurotransmitters.
Okay, so we've got all the pieces in place. Now for the main event. Let's walk through step by step how this incredible chemical handshake actually happens.
It all kicks off when that electrical signal, the action potential, arrives at the terminal. That's step one. That jolt of electricity is the trigger. Its arrival causes these special little doors, calcium channels, to swing wide open. And because there's way more calcium outside the cell than inside, it just floods in. And this rush of calcium, that is the final go signal. It tells all those little envelopes, the synaptic vesicles, to move to the very edge of the cell membrane, fuse with it, and then dump their chemical messengers out into the gap. This whole release process has a name, exocytosis.
Now, this whole fusing process isn't just random bumping around. It is incredibly precise. You've got this amazing set of proteins that act like a molecular zipper. They're designed to find each other, lock together, and physically yank that vesicle into the membrane, forcing it to release its contents at exactly the right spot. It's basically biological nanotechnology.
So, the message is sent. The neurotransmitter molecules float across that tiny gap, and this happens incredibly fast, by the way. On the other side, they find specific receptors they can dock with, and this is a very precise fit, like a key fitting into a lock. Only the right chemical key can open a particular receptor's door. So the message gets delivered. The key is in the lock. But what does the message actually say? It turns out that these chemical messengers really only deliver one of two very simple but very powerful commands. And those commands are basically this: fire or don't fire. That's it. An excitatory synapse gives the fire signal, which encourages the next neuron to pass the message along. And an inhibitory synapse does the exact opposite. It sends a don't fire signal that makes it less likely to activate.
Let's look at that fire signal. The technical term is an excitatory postsynaptic potential, or EPSP.
When that neurotransmitter key finds its lock, it opens up channels that let positive ions rush into the cell. All that new positive charge starts to cancel out the cell's natural negative charge, pushing it closer and closer to the tipping point it needs to fire its own signal.
So what about the don't fire signal? Well, that's an inhibitory postsynaptic potential, or IPSP, and it does the exact opposite. Here, the neurotransmitter opens up channels that either let negative ions in or let positive ions out. Either way, the inside of the cell becomes even more negative, moving it further away from that firing tipping point.
So you can see it all laid out here. EPSPs are the go signals, the gas pedal. IPSPs are the stop signals, the brake. Now think about this. Every single neuron in your brain is constantly getting hit with thousands of these go and stop signals at the same time. And its decision to fire or not is just the sum of all those inputs. All the incredible complexity of your brain emerges from this simple, constant voting process.
This whole system is so elegant, so efficient, but as you can imagine, it's also incredibly delicate. So for our last section, let's take a look at what happens when this intricate chemical handshake gets broken.
And we're going to use a really dramatic, real-world example, botulism. It's a very serious illness caused by a toxin that has one specific mission: to sabotage this exact process of communication between your nerves. And its attack is unbelievably precise. Remember that molecular zipper we talked about, the proteins that pull the vesicles into the membrane? Well, the botulinum toxin acts like a pair of molecular scissors. It finds one of those key zipper proteins and just snips it. Without that piece, the vesicles can't dock anymore. The message can't be released, the synapse goes completely silent, and that's what leads to paralysis. So this tiny, totally invisible chemical handshake is the literal foundation for everything you think, feel, and do. We just saw how a single toxin can break it. And that brings us to a final, pretty deep question. If this is the physical basis of our minds, what does it really mean that these connections aren't permanent? What does it mean that they can be strengthened, weakened, and totally rewired just by our experiences, by the very act of living and learning?